Welcome to Lecture 20. In this lecture, we're going to do another example about magnetic dipole moment. Then we'll move on to discussing Ampere's law. In this example, we're asked to find the magnetic dipole moment, so that's mu, of the hydrogen atom, where a hydrogen atom consists of an electron circling a proton at a distance of 53 picometers with a speed of about 2200 kilometers per second. This picture doesn't specify the direction of the electron motion, so I'm just going to assume it's in the counterclockwise direction. Okay, we're asked to find the magnetic dipole moment. Our equation for magnetic dipole moment is that mu, the dipole moment, is equal to the current times the area vector. Let's deal with the current part first. What we know about current is that it's charge divided by time. So how much charge passes over a length of time. The charge that's moving around is the electron that has an amount of charge equal to minus the fundamental charge. Okay, what can we do about t? Well, we know that speed is distance over time. That means time must be distance over speed. What is the distance? Well, when the electron goes around a circle once, the distance is the circumference. So then we can say our current is minus E times V over 2 pi R. We know V, we know E, and we know R, so we can go ahead and find our current. What do we mean by the area? Area is a vector. The magnitude of the area vector is pi times r squared. We are going to discuss direction, but let's finish off with the magnitude first. So the magnitude of our magnetic dipole moment is the magnitude of the current times the magnitude of the area. The magnitude of the current means the positive value, so that's minus EV over 2 pi r, times our area, which is pi r squared. You might notice that this simplifies a little bit. Our pi's cancels and one of our r's cancels to leave us with E times the speed times the radius divided by 2. For our numbers here, E is 1.60 times 10 to the minus 19 coulombs. R is the radius, 53 times 10 to the minus 12 meters. V is the speed, 2200, extra 2 in there, 2200 kilometers per second. So 2200 times 10 to the 3 meters per second. Once you pop all those numbers in there, what you should get is 9.33 times 10 to the minus 24. And the units, since magnetic dipole moment is current times area, the units are amps times meters squared. We're not finished the problem yet because we still have to find direction, and we'll do that on the next slide. Let's use the right-hand rule to find the direction of the magnetic moment for our problem. So we have an electron coming around in a circle. To use your right-hand rule, remember you make a circle with your fingers that matches the current direction. So our charge is moving this way. I'll make a circle that reflects that way. Your stuck out thumb represents your magnetic moment. That's coming out of the page, but we have to think critically about what we have here. An electron is a negative charge. Remember, our convention for current is what direction a positive charge. So if a negative charge comes around this way, the positive charge would be going around this way, and the direction of the magnetic moment is actually into the page. So we finish up our problem by writing our magnetic dipole moment as a vector. Mu equals 9.33 times 10 to the minus 24 amps times meters squared, with a direction of into the page. If you prefer, you can define a Cartesian coordinate system and include unit vector notation there. Here's a homework problem for you to try. It's not too tricky, so I won't go through it in a video, but I will post a solution if you want to compare your results to mine.